Hey, this is Mr. Peterson. This screencast is about the properties of water and how it allows life on Earth. So water is pretty important, right? So it keeps things green. We like to drink it. We like to swim in it. We like to run on it, right? Those liquid mountaineering guys. And it all depends on the special bonds between water, which are also set up by the intermolecular. So within the water molecules, those bonds in water molecules that help set up the bonds between water molecules. So water has slightly charged regions, and that's because of polar covalent bonds. And those polar covalent bonds set up positive and negative regions. We've seen that when you played with the models, so kind of like a magnet. Not that water is the north and the south, but it has opposite charges within it, within the different parts of the molecule. So what's a polar covalent bond? So a polar covalent bond is the bond between the hydrogen atoms and the oxygen atoms. So covalent bonds are sharing of electrons. And oxygen is such a large atom compared to hydrogen, it doesn't share the electrons very evenly. So because electrons have a negative charge and oxygen has lots of protons in it, the protons pull the electrons closer, and oxygen tends to have a slightly negative charge. Well, since hydrogen has lost its electrons, the shared electron, it tends to have a slightly positive charge. So that's the polar covalent bond. Now it creates some interesting scenarios when you bring water molecules close together. And you saw this with the modeling, that hydrogen and oxygen are attracted to one another. Well, it's pretty obvious to see it has to do with their charges being opposite. We put a whole bunch of them together, and all of a sudden we've got a whole lattice of molecules that are connected with hydrogen bonding. And it's really about the hydrogen bonding that allows life on Earth to happen, that creates amazing properties of water. And so that's what the screencast is about. So the hydrogen bond is the connection between water molecules. So they always orient themselves, and you saw this with the models. They always orient themselves hydrogen to oxygen, oxygen to hydrogen. And it causes those properties of water. So surface tension. And the surface tension aspect has two important components of it: cohesion and adhesion. So here's a water strider, a small insect. Why doesn't it sink? Why doesn't it sink? So it has to do with the cohesive properties of the water molecules underneath its feet. So if we zoom in and say that green arrow is the water strider's foot pushing down on the water molecules. The water molecules, notice the way they're oriented, positive and negative, positive and negative. They have a strength between them that allows them to fight that force of pushing down. That's surface tension. So the tension between the water molecules at the surface of the liquid. And it's like a skin, if you want to think of it. That's hard to break, at least for those water striders. For us, not so much. So surface tension, cohesion, adhesion. So if we look at water going up a tree, or the other day in lab where you saw water traveling up a piece of paper toweling, the water not only sticks to itself, but it also sticks to other things. It sticks to you, so it's adhesive to you. If we zoom in on this tree trunk and look at the water molecules, you'll see that the water molecules are not only sticking to one another, but they're also sticking to the inside of the tree trunk. So that's called the xylem. And so the properties of water allow water to kind of climb its way up the tree, especially when water up at the top of the tree is being used by the plant for photosynthesis and something else called transpiration. It pulls water all the way from the roots. Now, the phase changes of water, that happened way too fast. Come back here, come back here, come back here. So we've got the three phases of water. We've got solids, liquids, and gases. And look at, in order to change state, to go from a solid to a liquid, the water can absorb lots and lots of energy before it jumps to the next state. Notice on the y-axis there's a term called entropy. That has to do with the disorder. So as you go from a solid to a gas, the disorder or the randomness of the system, and that kind of makes sense. The water molecules in a gas, water molecules in the air, they're not together, so they're spread out all over the place. So their entropy is pretty high. So as you look across the graph, you can see it takes lots of energy, and the water stays relatively stable with regards to temperature. And then there's some big jumps. And that's the business of hydrogen bonding holding the water molecules together. So we take advantage of the ability of water to hold heat for a long period of time before it jumps from a liquid to a gas, and that's evaporation and evaporative cooling. So when you lose water through evaporative cooling, through sweating, the water molecules heat up to the point where they change from a liquid to a gas, and when they do that, they take some of that heat with them, and that feels cool. That's the cooling. That's the evaporative cooling. That's based on hydrogen bonds that are hard to break, and when they do break, they take some energy with them as they've absorbed the energy to change state. So what about ice? Why does ice float? How does that work? So it has to do with hydrogen bonds. So if we take a look at the density of water at different temperatures, as water is just in solution, just by itself, as it's liquid, it forms hydrogen bonds. But eventually it'll form a lattice that is less dense than the liquid water. And so ice crystals, if we zoom in, when water molecules slow down, it'll form ice crystals between them. So as heat is lost, eventually they slow down and they lock into place. We form hydrogen bonds that makes a crystal lattice, and that makes ice. It's less dense, so it floats, because there's more space between the atoms than when it's liquid. So you heat up ice, and what happens, those hydrogen bonds break, and it eventually goes back into solution. And those hydrogen bonds, if we watch this again, watch it again, see how they're far apart? And then they warm up, the hydrogen bonds are broken. So notice the hydrogen bonds are going away as the sun heats it up, and it becomes more dense. More dense. Kind of crazy. So hydrogen bonds and density all tied together. Water is also a polar compound, and that influences the way that it reacts with other things. It's a great solvent. What does that mean? It means you can make solutions with it. And so a solution is a homogeneous mixture, which means when you stir things together, you can't see them anymore. And solvents dissolve other substances. And water is pretty much a universal solvent. It dissolves lots and lots of stuff. So you take salt and you dump it into water. The water acts as a solvent. The salt is the solute. If we zoom in and look at what actually happens with the water molecules, the charges of the salt are pulled apart, and that's dissolving. So you're watching dissolving happening right now, much slower than it actually does happen. So notice the way the water molecules arrange themselves around the positive and negative sodium, positive sodium, and the negative chlorine. So those are hydration shells. So that's what happens when you dissolve things in water. Some compounds don't. So think about that in the lab, in the water lab. What did we see that didn't dissolve in water? What did you see that water didn't interact with, it didn't mix with? So think about that. Which stations in the water lab were those? So there's some hints. So if you take some oil and you dump it into water, you'll see that it forms layers. You stir it up, and what does it do? It forms layers again. Why? Because, well, water's polar, it has charges, and the lipids in the oil don't. No polar bonds there, so non-polar. No charge on that. So water has some really important properties. Number one, polar covalent bonds, that unequal sharing of electrons. Number two, the hydrogen bonds between the water molecules, not within the water molecules, but between the water molecules. It sets up all these properties: cohesion, adhesion, specific heat, density, and universal solvent. So really important properties of water. Hope that helps.